Okay, now for part 3. This one's kind of an insane problem. We have a way too big snow cone. I don't know if you guys have eaten a snow cone before, but it's really just sugar, frozen, sugar water. So this is a way too big snow cone, has a top diameter of 24 centimeters and a height of 30 centimeters, and we're filling it with liquid. The radius is increasing at a rate of 1.2 centimeters per second when the height is 15. So we're going to try to find out how fast the liquid is being poured in, which is really just dV dt. So the first thing I'm going to do is, like before, I'm going to draw myself a diagram, an oval for the top, a dot at the bottom as my apex. There it is. And then I'm going to fill in the dimensions. And so in this case, the radius is 12 centimeters, half of 24. And the height of this thing is 30. And remember that the height is measured as a line from the center of the circle to the bottom. And remember that we're going to be using some similar triangles. So there's our diagram. Next is the rates, and we've been given dr dt as 1.2 centimeters per second. And we're supposed to find dV dt, the rate at which it's being filled when the height is 15. And that's what we don't know. Okay, so the next step is going to be to write an equation. So the same equation as we've been using, 1/3 pi r squared times h. And in this case, we want to change this into an R problem. And the reason we want it to be an R problem is because we've been given dr dt. And so what I'm going to do is my little key over here of height to radius is 30 to 12, or if we reduce that, 5 to 2, dividing them both by 6. Height to radius is 5 to 2. That means that height is going to be 5r over 2. Okay, and so like before, I'm going to substitute that in for height, and now I'm going to have a new equation, or a more applicable equation in this case, r squared, and instead of height, it's 5r over 2. I'm going to simplify that, so it's 5 pi r cubed over 6, and this is now my equation. So if you're keeping track, we want a drawing, we want the rates, and now finally we want the equation. Okay, and then the next step is we're going to differentiate both sides with respect to time. So I guess I can fit that in under here. dV dt is on the left side, and then 15 pi r squared over 6 dr dt. That will simplify a little bit. Dividing that by 3 gives me 2. Dividing that by 3 gives me 5. And so our simplified dV dt is going to be 5 pi r squared over 2 times the rate at which the radius is changing. And so now I can solve for dV dt evaluated when h is 15. And I think you're going to see a little problem here because there's no h's in here. It's only r's. My pen has quit on me here. Let's see if I can get it back. No r. So what I'm going to do is I'm going to go back to this original little relationship that we had when height is related to radius as 5r over 2. And so if I have 15 equals 5r over 2, that means that r is 30 over 5, or r equals 6. So that means something kind of nice, that when height is 15, radius is 6. And if you're looking at the cone, you can see that similar relationship, 30 to 12, 15 to 6, Yeah, that makes sense. And so now, instead of r, I'm using 6, and then dr dt was 1.5. And this is all divided by 2. And so when I plug that into my calculator, h at 15, or which means r at 6, then I get 3, I lost it again. I think my stylus is out of juice. 339 centimeters cubed per second. And if you'll remember, 339 centimeters cubed would be roughly 0.339 liters, not roughly, exactly. So we could say that this is 0.399 liters per second. So about a third of a liter per second is our change in volume as a function of time when height is 15 or when radius is 6. Now I've switched it into liters just because that's kind of easier for me to imagine than it is in centimeters cubed.